So our first speaker this afternoon is Leonid Chekhov from Michigan State. We'll speak about Poisson, groupoids, and cluster algebras.
Yes. So I didn't. I will not write the title of the talk on the blackboard because I forgot it anyway. But really, it's related to construction of groupoid. And actually, I also want to mention that really this construction that I'm about to present today, at least the first part of it, was definitely the topic of my very last conversation with Kirill in Sheffield. I think it was quite a long ago, maybe 2017, something like that. And Kirill, of course, well, made a major contribution to these constructions, and especially to related Poisson constructions. So I also must confess that this part, at least the first part, is it's relatively foreign field for me, because my main expertise is not here. So just I will start with presenting this construction, which is rather old, and then I will come to some new results, relatively new, that's supposedly to be easy to comprehend in this audience, because I probably cannot say many things, or can drop some definitions, but some definitions I still need to present. So we start with the definition of a groupoid. So something that everyone here, I think, is knows. So we have a groupoid over a set, gamma naught is a pair with operations. I will just introduce some operations that play a prominent role, namely the source and target map. And we also can define multiplication on the corresponding set. So we say that for gamma 2, that is a pair of these objects, ordered pair. And such that the target of X is the source of Y, we can define a composition. That's why it's not a group and rather is a groupoid. So multiplication M, as usual, for any pair satisfying this condition. And we have two more maps. One map will play a role, identity map, so we can always map from gamma naught to gamma, taking some special transformation. And we have inversion, so inversion possibly will not play a very important role nevertheless. So let's so it's all natural. And these maps, they have all how we call natural properties. So it's natural properties of associativity. Identity inverses and so on. So this is just a general construction, and actually my example today will be a special occurrence of this construction, which is, so consider a unipotent matrices, triangular n times n, well, n, okay, which I denote by some reason this a by this a, and we denote the groupoid on the pairs of B and A, where B is basically it's a G length, but for possibly for purpose of today's talk, it will be yes, let it be just GLN matrix, such that, well, we have a source map of BA is just mapped to A. So let's also declare the corresponding set of these matrices to be, well, I will not use any index, just A, B will be a set of matrices of form such that they have units on the diagonal and zeros below. So this is source map, target map. Again, is just B transposed. And we impose the restriction that this map itself belongs to the same set. So we obtain the matrix of the same form. And of course, this imposes restrictions on the corresponding pairs of these matrices, B and A. And these restrictions are, if we want to solve them in general, they are, especially in this group setting, they're quite involved. So far, of course, there is no general formulas that solve this, but nevertheless, so about multiplication, it's easy. So we just have two pairs. Well, basically B1. So we okay. So yeah, I will write it this way. So this is actually A2, B2, and A1, B1, and the result of multiplication is basically just the pair A, B1, B2. I will not write identity is easy. Identity is just that we map A to AI. So of course, this equation can be always solved with identity matrix for B. And now we define something more. So we define actually algebraic operations. So instead of considering the groupoid, we consider the algebroid of the corresponding form. So we just introduce two operations, dA, that is now I will, so we can think about B as an exponential of some G. Then we have the algebroid condition linearizes on the set of these G's and A. So we have GA is mapped to the tangent space of this groupoid, of this group manifold, and such that G is mapped to, not surprisingly, AG. So by some condition, yes, it's by some reason we consider it's for B transpose plus GTA. And we also introduce the map from the tangent space to this manifold. So this is basically, we think about omegas as just strictly upper triangular matrices. So this is what we call PA omega. So it's mapped actually from cotangent space into GA such that again omega is mapped to, well, let me write it in terms of spectral projections. Omega A minus P plus 1/2 omega transposed A transposed. Where these P plus and minus, actually they are projections such that, well, I will write it specifically as for P plus 1/2. So it's multiplied all elements on the diagonal by 1/2. All elements above diagonal remains the same, and it just equate to 0 all elements below. So this is a projection. It was a nice paper by Alexei Bondel in 2000, where he actually solved this condition. Well, by introducing this basically solution. So we can parameterize algebraic solutions to this equation when we just consider B, well, some small matrices close to the unit matrix, if we just make this projection. So far it was about the corresponding so far it wasn't, it was just a purely classical construction. But now we are coming to the domain of Poisson bivectors, and actually there exists. So we can introduce the Poisson bivector P, which is, as usual, it's maps from the direct product of cotangent bundles into C infinity of A, such that if I have a pair of these omegas that we have here, I will leave this formula because I will need them during all this talk. They mapped into this trace form where we have just omega 1, and then we have action of these two operators on omega 2. Just well, some linear algebra construction. So there will be a lot of linear algebra constructions here. What is interesting in this map is that it can be proven that it's skew-symmetric. It's not so obvious, but it's also not a very long exercise. Again, in linear algebra. And we can actually identify the bracket. So now I'm coming. So I'm not so much a symplectic boy. I'm more Poisson boy. And we come to the bracket between elements. So now we have Aij elements of the corresponding matrix, and we can define explicitly the Poisson brackets between these elements is just, so we just replace the corresponding omega 1 and omega 2 by the corresponding differentials, dAik, which d over d dAjl of the corresponding trace. Okay. Now we come to definition and construction of a Poisson symplectic groupoid. I will just present it here, or maybe there, right? So we have a Poisson groupoid, and this is construction mainly due to Weinstein. Mikami, and in part also by Kirill. And it's also quite an old one. So it's 80s and 90s of previous century. So we have that gamma is a symplectic manifold gamma omega twiddle, where omega is a symplectic structure such that the graph M, that is, again, this is a triple now of objects. So X, Y are corresponding pairs. So we can always think about them as the corresponding pairs in the definition of the groupoid that is hidden now by that whiteboard, blackboard, sorry. And this is belong to the direct product of gamma, gamma, and gamma, where, of course, this X, Y, this pair belong to gamma 2 of the graph multiplication. And M is a Lagrangian submanifold. Of the triple gamma omega, oops. And gamma minus omega. So assuming that we have the corresponding Poisson structure, Then we, so assuming, so, sorry, omega is Poisson structure, dual to omega twiddle with some conditions of course, invertibility and so on, we have the following statement. We have that, again, proposition by Mikami and Weinstein, again, in the paper of, I think, 88, is that first, E of gamma naught is Lagrangian submanifold. So since that, it's actually, it makes sense to derive the corresponding brackets of quantum relations on the level of not of the pair B and A, but on the level of A itself. So we can always reduce the problem just to the Poisson or quantum structure on the level of these upper triangular matrices. Second, we have that inversion I is anti-symplectic. Diffeomorphism of the corresponding pair gamma omega twiddle. And the third condition, which is also will play an important role for myself in the rest, is that for any pair, the tangent spaces Sx and Tx are symplectically orthogonal. In other words, if we formulate this in terms of the corresponding source and target maps, so if I have a source map BA equal A and target map BA is above, they must Poisson commute. Yes, elements, so pairwise elements, so everything commutes, so they just split. The corresponding structures just split. It's a good question. We'll see. We'll see, because my next step is how we can actually produce these structures. What is the way? Again, so it's very explicit construction. So that's, I reserve this blackboard for it. So now let's come to some more specific formulas and to more specific statements. So we start with matrix B that is satisfying. I always uncertain what is Lie Poisson and what is Poisson Lie, because one is quantum and another semi-classical.
May I interrupt you and ask
Yeah, sure.
a stupid question about the beginning? So you said your groupoid is defined on the direct product, or it's not direct product because B cannot be arbitrary.
No, of course not. Of course not.
Where
So it's actually inclusion. Yes. So yeah.
inclusion.
Yes.
So A can be arbitrary, but B not.
A can be arbitrary, B not, but B is not defined by A.
But class of B is defined by A.
Class of B is. Yes.
Yes, restriction. But where this groupoid structure comes from is simply is it a kind of action groupoid or restrictional action groupoid?
I may not be so good in terminology, but
yeah, it should be.
Yeah.
It should be just. So you basically consider action of general action of one class of invertible matrices on the matrix of this class, and you just if the action exists, then
yes,
you just produce groupoid.
That's precisely my next step, because now we just invert the logic. We choose B, and then I say that if we choose B, well, in some, yes.
So why was he interested in this? What was his motivation?
Ask Lёша, I don't know why. Yeah, I'm not sure, because it was again, so it's all activities actually of 90s. Well, that's possibly true, Yuri. Yes. It comes from because I know this story from very different side. Because these algebras that appear here, they're actually prominent algebras appearing in geometry. This is what is called, well, it's just to, I didn't want to mention this because I was giving so many talks about it in past. But just to mention that the algebras that appear here, they have many names. It's, if I start, it's actually, I think the first were Klimik and who else? Also Ukrainian guy. I'm getting older. But it's also Klimik, Dubrovin, Ugalya. Then also it's from a more mathematical side. From physics side, it's also called Nelson-Regge algebras. And they are all the same. And actually, they are also from in the integrable system. They are called reflection equation. And so this is coming, this is here. And it just, you see, they appear in this business from many different ways of life, but they somehow converge into this definition. So let me just formulate one statement. So start with just the matrix B. So let's forget for a second about A. And lens B satisfies the Lie Poisson algebra. I will write it explicitly. And tell me if you are uneasy with these notations, because it's notations of in the direct products of spaces. Well, I will remind what is R. So R is R matrix. So R, it's not an R matrix, it's very specific R matrix. It's what is called a trigonometric R matrix without spectral parameter. So there is some generalizations of spectral parameter about which I will not talk today. Plus again, so this is expression. So the first ever actually R matrix that appear in the literature, I think, in Kulish-Sklyanin papers. Huh? Well, good. So this is notation for the tensor product. Often, yes, often I just, remove this symbol because it's, well, it's again, so again, to be honest, I just hit something.
Yeah, but tell them that it belongs to the tensor product, right? So this tensor product make yourself.
So it's, yeah, so it's a tensor product in SLN cross SLN. No, well, GLN, well, we don't put any restriction. In principle, they can even not, sometimes not invertible, so it's, yeah, yes. But with B, something different, because for B, we say B is, again, if we come to definitions, it's some EIJ cross BIJ. But these elements, they are not, usually they are not numbers in this case. They are actually operators in some, what we call a quantum space. Something, it's not rational numbers, so let it be just Q. So they are operators. And we just, so this is just a concise way of writing an algebra for the quadratic algebra for the corresponding elements of B. But again, so I confess that I will use, so this just means, for instance, that in quantum case, we cannot just interchange these matrices in the product. Would they be, for instance, just in the product of GLN? Of course, we can just write them in any order we want. But because they have these quantum constituents, they are not interchangeable. So this is what is called a quantum trigonometric R matrix. Possibly I shouldn't mention that R matrices satisfy Young-Baxter equations. That's possibly the folklore now. I hope so. Is it?
So Young-Baxter more or less implies one character of elite property for B.
Yes, yes, yes. Huh?
Well, for the benefit of the audience,
Recall? Oh, okay. I will just make one statement. So we have this, if we have a tensor product of three spaces, then we have that R12, R13, R23 is equal R23. So R13 and R12, that's, I think, true.
So you put B, but it should be B1, and people can guess what is B2.
B2 is just, so it's the corresponding, huh? B on the top. It's just that it's, okay, so B1 is the one, yes.
No, but tensor 1, right?
Huh?
Now you need a tensor 1 in the.
Okay, so if we are in the tensor product of B2 and B1, of course we have, yes, we have just the unit in the corresponding space, yes. So if I.
In B1, it should be E tensor 1, then no, E tensor 1, tensor B. Right?
Yes.
Yeah.
Okay. Now, good. Okay, good. So this is Young-Baxter equation. One of them, actually, not. No. But what they say? What will be here? 1 and 2.
How will I multiply by I?
What do you mean?
is element of tensor product of 2.
Okay. It's a. Okay, so let's write this. Let's write what is this. Just carefully. So it's some IJKL. E IJ1 EKL2. And then in the quantum space which I hit here, it just multiplied by BIJBKL. And if I swap this, so basically this part remains the same, only this order is changed.
How you multiply it by R matrix?
R matrix has no quantum, it's purely classical. It's identity in quantum space.
It means times tensor identity. R should be actually R tensor identity.
Yes. So in the quantum space,
R23 or something is 1 tensor R.
no. So here we have a triple product of spaces, 1, 2, and 3. So and then we again, so recall that we can just. This is also called a braid group action. So we have this, then we have that, and then we have the last one is here. So this is the first product, and this first product is equal to oops. So remember that it's also prominent in this braid group action. So if we have two different braidings, they produce the same result. So if I now identify each crossing with the corresponding product of R, so here, for instance, for the third space, it's just unity. So this is basically a graphical way of describing the Young-Baxter equation. Okay, but let's move, because otherwise we'll we'll be lost. Maybe I will, so this will probably don't need, because I want still show you something hidden there, and I don't want to make it available until later in the talk. So, so we have this relation. Let's keep them. Let's keep. So, and what we then have? Let's just look at this formula. B transposed belong to this set. And now just say, so let's take B some matrix in general position, almost general, as we'll see. And we just say that this product of matrices has this structure. It has, in principle, we know that it has units here, but let's, for a second, I replace these units by some symbols that will still didn't fix. Some numbers, non-zero numbers. That's the only condition that I require. Here we have zeros, and here we have something, anything. Now let's B belong to SLGLN.
Is there a restriction here?
Huh?
Is there a restriction?
I waived so far. I waived restriction at this moment, because now I just say differently. I say, okay, A we know A is a matrix of particular form. So now instead of saying that elements of B are restricted by elements of A, I say vice versa. I say Okay, so let's B be anything. And now what's about this A? What A can we? We'll have a couple. Well, so what is written here is actually a linear equation on elements of A, because we have a condition that elements with I greater than j are zeros. And you see that we have as many A's here as a number of these equations. And it is inhomogeneous because we have these units. So we can actually solve it. Solve with respect to A. So we can write that f a I j are some functions of matrix elements of the matrix B. And well, we have this algebra. We can write it explicitly. I just didn't do it, but in principle, it's just famous, two famous expressions, not too well. It have just basically two terms in the right-hand side. So we can address the problem. We can ask what now is the algebra of these elements induced by this standard Lie-Poisson algebra. That's we just postulated, this one. B is the same as here, B. So B here is the same EIJ, except that I didn't put any restriction on B.
And what is your quantum space?
Quantum space. No, quantum space is this B, are this B.
So you don't specify.
No. I know only the algebra between them, actually. Well, it's a matrix. No, why? It's a matrix. It's just matrix written in this form. So we can all. So EIJ.
The answers are not commuted. It's B. It's a matrix which enters subject to these commutativity conditions, right?
Yes.
And therefore, AIJ will also be some subject to some conditions which you are going to calculate.
So these functions are not normal functions. They are the ordering problem. AIJ equal to Fij of B.
Some
There is an ordering problem. You're right, but so far we hide it under the carpet.
Yeah.
But you have Poisson-Karébbergov with property.
Yes, we have. So that's we know that it's consistent at least. So they satisfy some relatively simple algebra, which if I remember, it's in a Poisson form. So if you want, I think it's something like that. So we just have to interchange and write that it's something like theta. I must confess I don't remember it by heart. So it's
some quadratic Poisson break.
Yes, and we have to interchange indices correspondingly. So I think that we interchange depending on either this BIL, BJK. No, never with this. So only no. It's even simpler. Sorry. It's theta, I think. I minus K minus theta, J minus L, and then we just
It's Poisson
It's
bracket.
Poisson bracket, so we can quantize it. We can quantize it. After quantization, well, there is a consistent quantization, which I don't. So these are quantum relations with this R-matrix. So I just write simpler Poisson bracket.
So it's Poisson B, therefore.
B, yes.
Now, I understand. So it's
B,
B Poisson B.
L, B, correspondingly KJ. Yeah. So this is a semi-classical version of these relations.
So it's quantum group. So what you wrote was quantum group, but then it's a Poisson B algebra relation.
Okay, but I think that I still need to present the results. So just theorem that we have is that if we define, so if you write this matrix A, again, in this following form, 1, 1, and here I have these functions Fij of B. Then, well, we have several statements. First statement is that these elements that we denote star I are equal to 1, provided all Casimirs of B are equal 1. I didn't say what are Casimirs. So Casimirs of B obtained by, so these Ci are ratios of minors. Ratios of minors in these complementary squares. So if all these ratios are equal 1, then all these diagonal elements here are units automatically. Second, I don't know what to do because I have something hidden there. May I just erase this Young-Baxter part because it's pretty much standard. So first, second, B. If I consider now a quantum relations between the corresponding, now I say these are elements of this matrix. So let's call it a matrix F. I don't, because something, well, I can, but it's actually dirty. Не видно, sorry. Okay, I think it's, okay, I can leave it a little bit. So number B is that this matrix satisfies the quantum reflection equation. Still, oops, R minus 1. So our matrix is always the same, just this one. Gamma, actually this pair B and F has a closed algebra. So we have B1, same R matrix, F2 is equal F B1R, RT1 here. Part T1 says this stands this symbol stands for partial transposition. Transposition only with respect to the first space. Just matrix, just formal matrix transposition. Huh?
The minus of field property one?
It's, yes, it's actually, so it doesn't matter when we write it for the matrix itself, because these operations commute. So total transposition commute with inversion, but with partial transposition, we must be careful. So it's actually transposed, yes. And delta. Finally, if we consider a map F to F twiddle given by VF V transposed, then we have that F and F twiddle commute. So, and finally, the last is that the algebra of this F twiddle is the reflection equation itself. Stop. Must be careful with these twiddles. So obviously, this construction satisfies all conditions of a quantum groupoid.
Meaning?
Well, if I come back to where I have it. Yeah.
Is your base of your groupoid also quantum, or only the arrows?
Basis. Well. What do you mean? No, Poisson. Well, okay. So, well, for me, quantum groupoid is actually basically the set of these conditions, at least in this case.
But what is the definition? It's a theorem, right?
Well, it's a theorem definition that the quantum groupoid is a quantization of Poisson groupoid. Some natural, because in any natural quantization, things that were commuting must commute in quantum case as well. Right, and that's what we observe here.
One can independent. First of all, the most general pin nodes, the most general definition of quantum groupoid pin nodes. Where's pin? Okay. So anyway, so you can define well in two cases. If a base ordinary set, well, a set of objects, then you just mimic the axioms of groupoid, axioms of category by like you do Hopper algebra instead of a group, right? So you reverse arrows and replace direct product with a tensor product. Basically, you mimic what you do for Hopper algebra. But if you replace the base, your base becomes an algebra, and well, it's more or less the same, but slightly more complicated.
But here, probably the base was A, right? And this is common now.
So the question is whether for him the base is the algebra or a set.
No, but look, A is F of B and B are quantum, so.
It is groupoid of what over what?
Well, it's actually both, because what I didn't mention. What are these expressions? That's what I want. That's something that I wanted to say and to stress, that actually these expressions that we have here, they are polynomial. They are polynomial modulo against these Casimirs, but Casimirs are commuting elements. So if we consider this A, they are polynomials. Even I can say with positive coefficients of the corresponding Vij, maybe modulo some Ci to some integer power. So Ci to, I don't know how to write it. So Because all these expressions are polynomials in B, then, well, basically we don't have an issue of translating from manifold to an algebra. Would we have some division or would we have some rational function? That would be a problem. But that's some advantage of this construction, that indeed we have only polynomials.
So the basis of the point is the algebra generated by Aij.
Yes.
And the functions of the groupoid itself are generated by Aij and Bij. No. What I'm just saying that we think in terms of functions, which are non-commutative algebras. So non-commutative algebra generated by A and B together, it corresponds to groupoid. Groupoid itself, the set of arrows. Only to A corresponds to the set of objects.
Yeah. So actually, let me just let me spend 2 minutes on actually. So this there are some different opinions where it was known or it was not known. I don't know. So this is probably the right audience to be asked about. If anyone ever, so this, just this construction, just this theorem, for instance. Okay, because basically I'm not claiming, it was in my paper with Marta, but I'm not claiming that we just did it from scratch, because most parts of these constructions were available, I believe. What is new actually is realizations of this B. That's the last part. So I think that I can remove this. How we can construct elements of this matrix B, and for this we have actually, I will say, cluster algebras or planar networks, direct planar networks. Again, what is a planar network that produce elements of this B? For instance, I will write it for n equals 3 case. So how it is going? So it's I'm sorry, I have to be probably sketchy at this point because running out of time. Well, probably even not that much my fault. There were many questions, which is good. But just recall, so we can actually by any planar network, we are able to construct the corresponding, so the dictionary is such that, so we have a planar network, we associate some quantum or classical variables with cells in this network. And we have a commutation relations being quantum or Poisson if I have, so you see in this network, I have white and black vertices. So if so for two variables separated by the edge joining vertices of two different colors, we have non-trivial quantum or Poisson relations in this case. So if this is white, then I think xj is q xj xi, something like that. If vertices are of the same color, then they commute. And there are some additional rules when we have half edges. So then we have basically half of relations. Again, because of lack of time, I will not write this. Then we can define, so if we have sources and sinks, we can define what is called a transport matrix is the sum of all passes from B to A of what is called quantum weights enumerated by these passes. For instance, if I have this pass, I associate with this product of all variables on the cells above this pass. So for instance, this omega B to A in this case will be just some ordered, while ordered product of these variables. And we have sum over all these passes. So actually, it's interesting. It was on the table for a while because it was observed by Fomin and Zelevinsky even before they invented cluster algebras. So it's a work of 98 that these elements, so we can parameterize this element this way. And actually, they considered only classical case, but in quantum case, we can also say that thus constructed transport matrices satisfy exactly the same relation. So we can provide, therefore, a cluster. So we associate cluster algebra variables with these variables X, and we can actually parameterize. So we can identify these transport matrices with the matrices B for any planar network. So not only for this one, it's actually works for any planar directed network under very mild conditions. Okay, so how it's all related to A's? And for this, yes, I saved this. So actually, this is, so we can, it's just experiments so far. Experiments where all these variables are just equal to 1. Numbers here are indicate actually all elements here are Laurent polynomials in this axis. Wait, they are polynomials, they become Laurent polynomials if we normalize by the conditions that determinant is 1. So, but basically, again, it doesn't affect much the construction. So numbers indicate the number of terms in the corresponding polynomials. For example, you see that for well, of course they are quantum at the end of the day, but now we just forget about everything, so we just collapse everything to some two example. In this two example, we just calculate how many terms do we have in the corresponding matrix element, because we know that all matrix elements are Laurent polynomials. All matrix elements for A, because they are Laurent polynomial, they are polynomials of polynomials, so they are still polynomials. So the same is true for A. So A now belongs to Z plus of the corresponding now axis, Xi. Now cluster variables. And you see what it just, so there is no still text about it, it's just some numerical experiments. Numerical literally, because there are just multiplication of numbers. And you see what is happening. So for B, if I consider networks of this sort, so I can generalize this for any n easily. For B, we have expressions for in the case n equals 3, B is like that, and A have this upper triangular structure. What is interesting is that this transformed A has very similar structure with the same numbers, except that it's swapped. It's you don't know the reason, it just happened. Numbers are 7 is number of terms in A twiddle transformed A 1, 2 in the corresponding matrix element. Because all elements, you see, all elements are polynomials.
So it's the sum of 7 terms, isn't it?
Hmm?
You mean the sum of 7 terms?
Yes. Sum of 7 monomials. Monomials in this cluster variables. And actually this, and you see that we have the corresponding numbers for 4 by 4, for 5 by 5 case. Well, and these numbers are very mysterious actually, because
What is curly M?
curly M, well, it's some, so we have that this B is curly M1, curly M2 times just this matrix of, just this sign matrix. And curly M2 is again, so I didn't write it here, but they are all almost the same as curly M1, if I can. So where? I have it for, so you see it's literally, this is almost the same matrix, just reflected with respect to the middle.
But we take a particular monomial in the case M1, 1, 1 is a particular monomial, or you take all monomials?
All possible, no, it's all possible monomials will have this the same number of terms.
Yeah, so M1, 1, 1, 1 is all possible monomials. And
What do you mean by all possible?
I don't know, what is M1?
It's just that we get it when xi, all xi are identical 1. So if they are not, they just appear here by their monomials. So it will be, well, we can easily evaluate it on the computer for just general x, it just, we didn't do it. And, well, that's the end, except that I still have a hidden, well, because there is another description which I unable to present because of lack of time, but there are many questions, so I like it. We can use, that's why I wanted to keep this M1 and M2, because if we just do it stupidly, introduce the network with these elements M1 and M2 here. And it's actually easy to observe that these matrices, in general case, they satisfy this set of quantum equations. And then if we just stupidly enough take this combination, then they will again satisfy the reflection equation. So it will provide another not groupoid representation, log canonical representation for the corresponding elements of reflection algebra. This is, and this is published. This is part of our paper with Misha Shapiro of 2020. And this is some mystery, a sort of mystery, because here these numbers. So it's the same. So it's the same statement that all these elements A, I, J, again the positive Laurent polynomials of xi, but numbers of terms are completely different. So this is, for instance, this For A3, we have this famous Markov triple. And well, all the other numbers, as you easily see, are just some binomial coefficients. But they don't satisfy the groupoid property. If I consider, there is no notion here of B matrix at all. We don't know what B is. At least we, I mean myself. Maybe someone else knows, but not me. Here we know B, it satisfies the groupoid condition, but however, realizations of algebras seems to be completely different. So there is some sort of mystery, but also I think some sort of satisfaction, because I was looking for this actually log canonical coordinates for reflection equation maybe for last 15 years. And constructing two different realizations in the course of 2 years is, well, I think some advantage. Okay, thank you.